Hi, this is Dr. Xu teaching design of experiments for engineering research. A simple experiment involves repeat the same test for a couple of times and see the responses. In this example, the strength of the material is tested for 10 times, and the results are shown on the right here. Most people will take the average of the strength and conclude that the material strength is the average result. However, there are much more information included in these 10 data points. In this video, we will use this example and introduce some of the basic concepts in design of experiments and find out more information and its meaning in the results. To test the strength of the material, basically you can prepare the material for testing. Each of the tests is called a run. So here, you can repeat the test procedure, and all these replications are called independent repeat runs. To complete all the tests, most of the time it requires a large number of runs. Here, the entire runs set is called the population. If 5,000 tests are required to complete all the tests, the population size is 5,000. Note that sometimes the population size is known, like here, but sometimes the population size is either unknown to be a large number or the size is infinitely large. This allows us to use statistics in designing and analyzing experiments. In this example, although it is possible to perform the 5,000 runs and find out the strength for each individual test, due to the time and cost restrictions, we are not able to perform all of them. We only randomly select and perform 10 runs. This 10 runs set is called the sample of the population, and the size of the sample is 10. So the size of the sample is 10. We would like to use the strength test results from the sample here, which has 10 runs, to estimate the strength in the population. The first parameter we want to estimate is the population mean using the sample average. The population mean, mu, is calculated by adding up all the observations in the population and divided by the population size. So in this example, you add up all the observations and divide it by 5,000. The sample average, y bar, is the sum of the observations in the sample and divided by the sample size. Here we have 10 values, y1 to y10, and divided by the size of the sample, which is 10. Note that mu is the parameter quantity directly associated with the population. We use a Greek letter to represent it. And y bar is a statistic quantity calculated from the sample. We use a Roman letter to represent it. We can only use the sample average to estimate the population mean. If each time we take a random sample of 10 and perform test for sample A, here you have 10 tests. Sample B, you have another 10 tests randomly taken from the population, and you can do it again. In sample C, you have another 10 random sample from the population. So now we will get 3 different sample averages, y bar A, y bar B, and y bar C. Most likely they are all different, but all of them are close estimate of the population mean, mu. Here we plotted the test values on this dotted plot and calculated the average to be 16.76. So we can guess or make estimation that the mean strength of the tested material is 16.76. Suppose we take another random sample of 10 and perform the strength test and take the average. It is now 17.63. We can do this again and calculate the average, and it is going to be a different value again. So as you can see, each time if we randomly conduct 10 tests and calculate the average, and each time the average value is going to be slightly different. If we repeat the above mentioned procedure many times, the results can be better illustrated by using this plot. The dashed lines is the true population mean, mu. This is the average for all the 5,000 tests. Each of the bar here represents the value range of the random samples in each sample test with 10 samples, and the blue dot is the calculated sample average. For example, we have done 10 random runs here, and the minimum strength value is here and the maximum strength value is here, and the calculated sample average is here. As we can see, if we repeat the process, each time we get a different average value, and they are scattered around the population mean mu. Statistically, the distribution of the sample average y bar is approximately normal. So it forms a bell-shaped curve centered at the population mean mu. This is called the central limit theorem. This statistical theorem applies to any types of population distributions and does not require the population distribution to be normal. For example, here the population distribution can be uniform, exponential, or log normal. Here represented the sample average distribution for different sample sizes. The red dashed lines are the perfect normal distribution referencing curve. As we can see, when the sample size is 2, the sample average distribution fit the normal curve poorly. So the sample average distribution is like this here, but the normal distribution is here. As we increase the sample size to 30, they all fit the normal distribution curve nicely, irrespective of their original population distribution. The normal distribution of the sample averages is centered exactly at the true population mean, mu. We would also like to know the standard deviation, sigma, of this normal distribution, as the mean and the standard deviation determine a normal distribution curve. For that normal distribution, we can calculate the standardized normal deviate value, z, to know how far away the current value deviates from the mean. This is also called the calculation of the z-score, and by doing this, we have converted a normal distribution curve to a unit normal distribution curve, like here, also called a standard normal distribution curve, with mean of 0, so centered at 0, and standard deviation of 1. So here is 1 standard deviation away, and here is 2 standard deviation away. And here is 1 standard deviation away to the left. Let's look at one example here. If the normal distribution has mean of 4 and standard deviation of 0.3, what is the possibility of a random picked value exceeding the value of 4.4? We firstly calculate the z-score. So z equals to the value 4.4 minus the mean, which is 4, divided by standard deviation 0.3 equals to 1.33. So on this plot, the value 1.33 is here. This means the value 4.4 is 1.33 standard deviation apart from the mean. The possibility of values larger than 4.4 is represented by this shaded area. We can use a standard normal distribution table to find the area on the right of the z-score 1.33. So we can use the table on the left to find out the area here. On this standard normal distribution table, the values here represent the area to the left of the z-score. So these values represent the area on the left of the z-score. So we need to subtract it from 1 to get the area on the right part of the z-score. So look at here, the z-score is 1.3, and the second decimal place is another 3 here. So we look down here, we find this value. This means the area to the left of the z-score 1.33, so this area is 0.90824. So this area on the right is 1 minus 0.90824 equals to 0.09176. So this is this area. So this equals to about 9.2%. This means in these normally distributed values, there is about 9.2% chance of a random chosen value to exceed 4.4. Go back to the sample average distribution. It's centered at the population mean mu, but we don't know the population mean because we cannot do all the 5,000 tests. So we can use the sample mean y bar as an estimate of the population mean. So y bar approximate the population mean. The standard deviation of sample average sigma y bar equals to the population standard deviation sigma divided by the square root of the sample size. In our example, this is 10. These two expressions can be mathematically proven. We just introduce it here without going into the details. Still, we don't know the population standard deviation sigma, which is the standard deviation for the 5,000 tested strength. So we can use the sample deviation S as an estimator for sigma. The sample standard deviation is calculated using this equation here. Each individual observation minus the sample average square and sum up all these values divided by n-1 and the square root of the result. Here the denominator n-1 is called the degree of freedom. This n-1 is used when the sample size is small, normally smaller than 30. Remember that we have talked about the distribution of sample average is near normal as the sample size increases. When the sample size is more than 30, the distribution is almost normal, but it is less normally distributed if the sample size is less than 30. See here and here. The actual shape of the distribution is related to the size of the sample. More precisely, directly related to the degree of freedom. This forms the t-distribution. For each of the distribution curve here, the concept is similar to that of the normal distribution, but instead of having a single normal distribution curve for different degree of freedom, we have different distribution curves. This forms the t-distribution. The t-distribution is mostly used in the design of the experiment, as most of the time our sample size is less than 30. So in the t-distribution, instead of calculating the z-score, we calculate the t-score the same way as we calculate the z-score. So the t-score equals to the value minus the population mean divided by the population standard deviation. For sample average distribution, it is centered at the population mean, mu, but we don't know the population mean. Again, we use the sample average as an estimate for the population mean. So substitute y bar into mu. And here in the denominator, we use sample average standard deviation. It can be mathematically proven that the sample average standard deviation is the population standard deviation divided by the square root of the sample size. In our example, n equals to 10. Again, we don't know the population standard deviation, so we use the sample standard deviation as estimate of the population standard deviation. The sample standard deviation is calculated this way. So this goes to there, and this goes to there. Let's look at the material strength example. The strengths for 10 randomly selected samples are shown in the table, and the question asks, what is the possibility of performing another 10 random sample test and the sample average is larger than 17? From the central limit theorem, we know that the sample averages form a t-distribution, so we can calculate the t-value of 17. So we will need to calculate the t-value of 17. Firstly, we calculate y bar. So y bar equals to the average of these 10 values, 16.8 16.85 plus 16.4 plus 17.21 plus you add the rest of the number plus the last number 16.57 divided by 10 equals to 16.764. So this number goes to here. Next, we will need to calculate sigma y bar. To calculate sigma y bar, firstly, we calculate the sample standard deviation because we use this sample standard deviation as an estimate of the population standard deviation. S equals to square root, the first value 16.85 minus the average 16.764 square plus the second value 16.4 minus the average 16.764 square plus you do this calculation for the rest of the numbers and the last number is 16.57 minus 16.764 square divided by n minus 1. The sample size is 10, so 10 minus 1 is 9. And the result is 0.316. So sigma y bar equals to S divided by square root of n equals to 0.316 divided by square root of 10 equals to 0.1. So now the t-score equals to 17 minus 16.764 divided by 0.1 equals to 2.36. So this means the value of 17 is 2.36 standard deviation away from the population mean of 16.764. Now we can use the t-distribution table to find out the possibility of t larger than 2.36. So this is t-value. So we want to find out the t-value larger than 2.36. So the area there. Previously, for the z-score table, we have a z-score corresponding to a possibility. For the t-distribution, the possibility is not only related to the t-score, but also the degree of freedom. The t-distribution tables are presented in different ways, but in this table here, alpha is the possibility. So these are the possibilities. And these are the degree of freedom, and the values in the middle here are the t-scores. So we know the degree of freedom is 10 minus 1, that's 9, and the t-score is 2.36. So we search this line. 2.36 is between 2.262 and 2.821. So the possibility is also within these two numbers. So the possibility is between 1% and 2.5%. So 1% to 2.5%. We can only get to this much accurate by using this table, but using a computer program, we can calculate the exact percentage to be 2.13%. So this area is 2.13%. This means if we do another 10 random tests and calculate the average of the 10 samples, the possibility of getting an average that is larger than 17 is only about 2.13%, which means it is very unlikely. Now we have constructed the sample average distribution model as a t-distribution curve. The middle here is y bar, so can be estimated as y bar. And the standard deviation can be calculated using the equations here. As shown in this plot, if we repeatedly compute the average from random samples, most of the time the sample average falls within this value and this value. the chances of values larger than that value and smaller than this value is small. If the shaded area between this YA bar and YB bar is 95%, so this area is 95% of the entire area, we say that the 95% confidence interval for the population mean is from YA bar to YB bar. Now let's see how to find the value of YA bar and YB bar. If the shaded area is 95%, the total area of the unshaded area will be 5%. So this area here plus this area here is going to be 5%. Because the curve is symmetrical, each side of the area is 2.5%. If we know the area, we can find the corresponding t-score, and then we can calculate the value. If we know the t-score, in this equation, we can solve the y value. So solve y equals to the sample average y bar plus t-score by sample standard deviation divided by the sample size. Let's look at the same example. The question is, what is the 95% confidence interval of the sample average? We have calculated sample average y bar is 16.764 and sample standard deviation s divided by square root of sample size equals to 0.1. So in this equation, we know y bar and we know this term. We only need to find out t-score. Now we know the upper area here is 2.5%. And the degree of freedom is 9 here. 2.5% is here. We can look down here and we have this number. So the t-score is 2.262. Here, YB bar equals to 16.764 plus 2.262 by 0.1 equals to 16.99. The lower area here is 2.5% as well. Due to the symmetrical shape and the middle here is 0, so the lower t-score here is going to be negative 2.262. So the YA bar equals to 16.764 minus 2.262 by 0.1 equals to 16.54. Therefore, the sample average 95% confidence interval is between 16.54 and 16.99. The generalized confidence interval is shown here. C is the confidence interval levels such as 95% or 99%, and the t-score can be found using the area of 1 minus the confidence interval divided by 2. So what does confidence interval mean? It means if we repeatedly perform 10 random samples tests for 100 times and calculate the average strength value, 95 times the value would be between 16.54 and 16.99. This also means that we are 95% confident that the true population mean, mu, this is the mean strength for the 5,000 rock samples, is within the value of 16.54 and 16.99. So to draw conclusions from the experiments we have done, we have tested 10 samples and the sample average is 16.76. Also, we are 95% confident that the material strength is between 16.54 and 16.99. A brief summary of this video: we have introduced the population parameters and sample parameters, and I have shown you how do we use the sample parameters to estimate the population parameters. Also, we have introduced the central limit theorem, which is basically the sample average is normally distributed. But for sample size that is less than 30, we use the t-distribution for the sample average distribution. Also, we have introduced the way of calculating confidence interval using the t-distribution curve. Okay, thank you very much for watching this video. This is Dr. Xu. I will see you in the next video.